Please welcome Mark Daoust.
All right, hi everyone. So, like they said, my name is Mark Daoust. I work as a developer programs engineer at Google. At my previous job, I spent most of 10 years building machine learning models. Building them, doing the calculus required to train them, then translating them between languages and between platforms. And I'm glad I don't have to do that anymore. TensorFlow would have solved many of those problems I was working on, and I hope it can solve some problems for you. All right, before I get into the main part of the talk, I just kind of like to test the audience a little. How many of you are already using machine learning in your products or projects? Okay, a couple. That's good. That's like 5 to 10%. What about using TensorFlow itself already? How many of you are using that for your machine learning? It looks like we have one or two. And what about TensorFlow serving? Have you heard of it or tried it out? Okay, less and less. All right, so this talk is split into 4 main sections. I'm going to start by covering the current state. 4. I said 4. 5 main sections. I'm going to start by covering the current state of machine learning and deep learning. Then I'm going to have a look at sort of the basics of TensorFlow, what it does for you, a bit of how it does it, and how it can help you. Then we're going to look at how to actually build a model in TensorFlow, and then how to serve it in a web scale application. I mean, obviously, this 4th section is the part that's most directly relevant to this audience. Just for this talk, I didn't want to assume too much prior knowledge. So we're going to do sort of the overview of everything before we get to actually serving models, which is probably what you're interested in. The last section, machine learning at scale, is going to be about exciting things happening in machine learning at Google. So, machine learning. Machine learning is basically, it's a gigantic field, but it can be summarized to, the simplest approximation is that machine learning is what happens when you realize that I'm not smart enough to solve this problem, but I have data, and I'm smart enough to build a system that can learn the solution from my data. All right, I'm going to be talking about one small branch of machine learning in this overview part. Since machine learning is a huge field, you can spend your whole life studying it. I'm going to be talking a bit about deep learning here. Deep learning is exciting because we've seen many breakthroughs come out of it in the last few years, especially when dealing with natural data, like sound and images, videos. But the progress isn't limited to these natural sorts of data. And it's not limited to these neural network models that I'm about to talk about. It's mostly powered by having computing resources and data. I mean, that's what really drives this. All right, so how does deep learning work? Mostly, it's just a question of having many layers of these neurons. I mean, they call this a neural network. It's a function that can learn. Right? You stack up layers of these simple weighted connections, and each node in the layer, it sums each of its inputs multiplied by the weight on the connection, and then it applies a nonlinear function to the result. We have optimization procedures that can look at this calculation and automatically adjust the weight to achieve the result you're trying to get. If you want to build a model of your own, you basically need 2 things, right? You need to rephrase your question, rephrase it as an equation, right? It's a little bit like playing Jeopardy. Remember in Jeopardy, you have to rephrase your answer in the form of a question. Here, you rephrase your question in the form of an equation. The simplest example of that is if you've ever done like linear regression, right? The thing you have to optimize is the sum of the square of the errors. Right, so you need something like that, and you need data, ideally lots of data. Data is what lets you optimize those weights to get a sane answer out of a system like this. And that's the basic trend we're seeing with these. That the model is your rocket. You need the computing power to build a large model, and your data is your fuel. And if you have enough data and a big enough rocket, you can go to the moon. So one example application is for image classification. Right, 5 years ago, just 5 years ago, this was a hard problem. I mean, this would have been a research project. But now it's basically solved. We have the optimization procedures, we have the libraries, and the computing resources to do it. Now it's simple enough, it's straightforward enough, it's well understood to the point where you can build your own model like this in about an hour, based on a pre-trained model, but it's not hard. If you see that TensorFlow for Poets code lab I mentioned at the bottom of the slide, you just need a few pictures in a few folders sorted by category, and you can retrain this to determine what type of flower a picture is of, or to determine if it's a hot dog or not a hot dog. Right, on the previous slide, I was showing sort of an artist's rendition of a neural network. Here, we've got a picture of an actual image classification model, a real model. This is Google's Inception v3. It has 25 million parameters. Relative to the previous slides, we've zoomed out quite a bit. Each block in here contains a layer of many of those little neurons we saw on the previous slides. And it's this sort of thing that now powers image search, for example. For those of you who are familiar with how image search used to work, right? Google would download the web page, read the text, look at the alt text, look at hints on the page as to what the image might be, and it would use that to return image results. Now, for image search, Google downloads the images, looks at the images, and if you search for cat, it returns the images that were pictures of cats. It doesn't return the images that were on pages that talked about cats, which is a bit more like what it used to do. Another great thing about this explosion of deep learning is that a lot of this stuff is getting open sourced. This Inception v3 model is available for download. You can go get it and do whatever you want with it and use it as a building block to solve bigger problems. We've open sourced many models like this. Google has shared a huge amount of research, and many of these are state-of-the-art in their respective fields. We already looked at Inception, but we've also open sourced, for example, natural language parsers for many languages. This artistic style transfer model from Magenta, which is computers making art, which is kind of fun. We've also open sourced models for audio generation, text summarization, and tools that are part of a translation framework. And of course, there are many more examples than just these, more than I can fit on a slide. But the key point is that there are open source deep learning solutions for many problems. And these break records relative to a couple of years ago. And using these as building blocks for harder problems, here's one really interesting example. This is a model called Show and Tell. It makes computer-generated captions. Right? On the slide, we see, on the left, a man riding a wave on top of a surfboard. I might have said he was riding the surfboard. And on the right, we have a person on a beach flying a kite. Right? This Show and Tell model is built out of that Inception image recognition model and parts of that translation framework I just mentioned. You put the two together, and instead of translating French to English, you translate image to English. And it's shocking that it works this well. And 5 years ago, it would have been inconceivable. Right? Another really promising direction for deep learning is assisting physicians. Diabetic retinopathy affects nearly 10 million Americans. If caught early, it can be treated, but if left untreated, it can lead to blindness. Eye doctors, ophthalmologists, diagnose it by looking at retinal scans. Last year, we published research based on that same inception model showing that ML can achieve accuracy on par with ophthalmologists at diagnosing this. Similarly, pathologists have a really hard job searching through scans of biopsy samples to determine which areas are potentially cancerous. It takes years of training to learn to do well. And we've released research showing surprisingly good performance on this pixel-by-pixel labeling task. And I say surprisingly good because on one measure, it exceeds the score of the average pathologist. Which, like I said, it may be a bit surprising because we use pathologists to generate the input data, but maybe it's less surprising because we had a lot of data and a lot of pathologists to do it. A third example where there's a lot of potential to help out in the medical field is with moles, right? We all have a few moles, little colored spots on our skin. If you find a suspicious-looking mole, you need to find a dermatologist to look at it. You know, sometimes the dermatologist can just look at it and see that it's nothing threatening. But maybe they have to take a biopsy and send it to a pathologist to determine the exact type and whether or not it's dangerous. This year, Stanford published research on how to build models that accurately handle that first stage of just looking at it and determining what it probably is and whether or not it's dangerous. And from a single image, they can tell you if it's something you should worry about or not. I mean, this isn't to lessen the hard work done by doctors or the hard research that had to go into making these things work, but all three of these examples I just mentioned are based on that same Inception v3 model. It's just a building block, and they all have huge potential to help doctors do a better job, right? Whether it's as an automatic and instant second opinion, or if it's just reducing the workload for these overworked doctors by potentially triaging the easy cases for them. Right, within Google, right, the fact that machine learning and deep learning seems to have so much power to solve real-world problems over the past few years, here's what's been happening inside of Google. This graph shows the number of machine learning model definitions that you can find inside of Google's code base as a function of time. TensorFlow was launched internally in Q3 2014, and the explosion after is for two reasons. I mean, first, it's that machine learning can be a huge help with lots of real-world problems, but second, it's that TensorFlow made it easy. I mean, we had model definitions before that Q3 launch of TensorFlow, but those were in a different system. It was called disbelief. It wasn't as flexible, wasn't as easy to use, so it just wasn't getting the traction that we were getting after launching TensorFlow inside. And if you look at the results, right, basically every Google service, these things you use every day, they're filled with machine learning. We have over 100 production projects that are using this sort of neural network technology. If you're using Google Search, it's had deep learning-based ranking since 2015. It's also used in pretty much any recommendation engine or speech recognition, smart reply, or translation. It's used all over the place internally. So we've seen a few applications of deep learning. And how do we solve these problems ourselves? All right, with TensorFlow. Let's talk about what TensorFlow is. TensorFlow is an open source machine learning platform designed for everyone. Right? It's meant to be fast, flexible, and production ready, and it's meant to scale from research to production. And when I say production, I mean, like at my previous job, I mentioned earlier, I used to translate models. I used to write a model in MATLAB and then rewrite it in C++ and then rewrite it in assembly to put on our microcontrollers. TensorFlow makes it so you don't have to do that anymore. Right? You write your code once and it works everywhere. If you measure by GitHub stars, TensorFlow is the most popular machine learning framework, if GitHub stars matter to you. We've had 17,500 commits since we open sourced it a year and a half ago, almost 500 non-Google contributors, some significant external commits, and we also see on GitHub over 6,400 repos with TensorFlow in the title. We've answered 5,000 questions on Stack Overflow, and we've had 5,000 bugs filed against us on GitHub. We get about 160 new ones each week. The people triaging those are working very hard to keep us from being flooded. So what does TensorFlow do for you? Right, well, it builds computational graphs. Right, you write Python code, and the Python code builds the graph. There are three major reasons to operate on graphs like this, aside from the fancy pictures that you can make from it. The first and kind of the most important reason is so that you can optimize the models. I mean, I won't go into detail here, but it does all the basic calculus that you would need to run the optimization algorithms that let you get a meaningful result. Right? You can do stuff like that yourself. I've done it before, but you don't want to. I don't want to. And getting your calculation into this graph form allows standard algorithms to run over the computation and figure out how it needs to be modified to achieve your goal. So the second advantage of having a computational graph like this is to optimize the calculations themselves. Right? Having a computation graph like this, you can easily tell by inspecting the graph data structure. You can tell which operations you can run in parallel because their inputs and outputs don't conflict with each other. You can also tell which operations you don't need to run at all because they're not required for the one output that you really want. And the third reason we make graphs like this is for portability. If we were just writing code in our language of choice, it would be much harder to get it to run on all of the platforms we want it to run on. TensorFlow is very cross-platform. And the TensorFlow graphs, the computation graphs that it outputs, are completely platform agnostic. It's a lot like many programming languages. There's effectively a language runtime that you install, and it's independent of your program. TensorFlow, because of that, TensorFlow can run on basically anything from CPUs to GPUs, your mobile devices, the Internet of Things, or custom hardware because of the pluggable interfaces. The example custom hardware there is Google's TPUs. These are tensor processing units. They're specialized hardware that we built at Google to run machine learning math faster and more efficiently. We might talk about them later if I have time. So because TensorFlow tries to support any platform, any language, well, because it tries to be very cross-platform, it also supports just about any language. Python is the primary language you would use it from. We have official C++ support, and Java support, and Go support, but there are also many community projects that allow it to be used from a variety of other languages. And trying to avoid any sort of lock-in for our users, right, that doesn't just apply to devices or languages, it applies equally to which cloud service you want to use. Right? Google, the TensorFlow team, recently open sourced their benchmarks, right? All the code is available. If you go to that link, all the code is available. You can download them and run them yourself. And you can run them on the Google Compute Engine or on Amazon EC2. It's up to you. We're not trying to force anything on anyone. Another significant development in TensorFlow recently is that we've launched TensorFlow version 1.0. And that's mostly because it's matured significantly since launch. enough that we're comfortable calling it version 1.0, or we're actually up to version 1.2 now. And one of the main promises from this 1.0 series is a stable API. So you can write code and be confident that it won't break going forward. OK, so now that we've talked about what TensorFlow does for you, let's talk about building a simple model. Here is a simplified representation of the TensorFlow stack, the software stack. At the bottom, you see devices. In the middle, you have the TensorFlow distributed execution engine. And on the top, you have language interfaces. TensorFlow is this big, powerful library built by smart people, does all kinds of fantastic things. But in the original Python front end, they only had the low-level interface. We've been working very hard to add powerful, high-level interfaces to TensorFlow. The simplest example is that machine learning involves a lot of low-level math. But you don't think of it in terms of that low-level math. When you think about a deep learning model, you're not thinking, do a matrix multiply, then do another matrix multiply. You're thinking in terms of layers or entire models. And being able to program TensorFlow at the same level you think about it can be a huge win. So we have high-level components for customizing your own models, but we also have these canned estimators. These are standard, well-understood models, and in a lot of cases, like most of the models I built at my previous job, these canned estimators have you covered. There are a short list of models that can solve quite a few problems. So let's look at a quick example, right? This is much simpler than the code we might have seen drawing the computation graph a few slides ago, because that slide was written in the sort of low-level TensorFlow. This one is focusing on the high-level TensorFlow. This is an example of what the code can look like. On the first line, we're creating a linear regressor. In this example, we're trying to learn car prices from descriptions of cars, where the description involves, the make of the car, the horsepower, the number of cylinders. I've left out the code where you describe, what type of inputs the model is expecting you to feed in. The make is categorical. It's chosen from a short list of strings. The horsepower is a real number, a floating point number. The number of cylinders is an integer. Right, so once you've created your linear regressor, you just say regressor.train, and you pass it a source of data. I've left out the code where we generate this data stream, but it's nice how simple this can be. Right? Here's your data, train for 10,000 steps. All the basic rigging, the boilerplate is done for you. The logging, the save and restore logic, so that if your computer crashes halfway through, you can pick up where you were training. All the setup required most of the setup required to run it distributed, it's all baked in to these high-level classes. All right, you hit train, and it trains. It prints out a bunch of logs. These text logs are kind of boring. We also have this tool called TensorBoard. Those high-level estimator classes, they also set up everything so that it can be used with TensorBoard. It's our browser-based machine learning visualization tool. It's kind of like an X-ray system for your deep learning model. It lets you interactively explore your graph, and it shows you what's happening inside your network during training and inference. It lets you explore your training logs. Here we see how the training error is reducing over time while the model trains. But TensorBoard isn't limited to simple line graphs. It has built-in visualizations for a variety of media types. This screenshot is from the embedding visualizer, showing how handwritten digits are clustered. And you see how obvious it is to pick out the couple of number 8s that look a lot like 5s. Right, so once you've gone back to TensorBoard and checked your logs, if you see that it's not performing at the level you expect, maybe you want to try a deep neural network instead of a linear regressor, it's not that hard to change, right? Since these models are relatively well understood, we're confident in having these high-level wrappers where you just say, yeah, I want a deep neural network, and I want it to have 30, 20, and 10 hidden units at the layers between the input and output. I mean, here I'm building something tiny, just 60 neurons in total, but these canned models have built-in scalability. We provide these classes because we use them internally as well. So, now that we have a model, let's think about what to do with it. Right, let's try to get it out into production. Right, we want to serve our TensorFlow. On the left of this diagram, we have our data scientist, we have our model, and we have our data. On the right, you have your application, and it wants answers. I mean, let's say your application contains a video recommendation engine. You open the app, and from a list of candidate videos, it needs to calculate the probability that you'll click each one. You probably want an RPC server in there. Right? That's pretty unsurprising. Right? Its job is to load the model off disk and make it queryable by the application. And while it's probably trivial for many of you in here to set up a simple RPC service, there are many subtle issues to serving these models, especially the large ones. Right? And we've been doing this for quite some time. So if you want to serve TensorFlow, I'm going to recommend using this program called TensorFlow Serving. TensorFlow Serving is a flexible, high-performance serving system for machine-learned models, and it's designed for production environments and optimized for low latency, because you all know how important latency can be when serving things real-time to users. Right? Like I was saying, Google has hundreds of products using machine learning internally. And the same way, we have hundreds of products using TensorFlow Serving. Right? So please benefit from our experience. We have gone through a lot of pain to make this into something that works well. I mean, there are many sorts of problems where if you just grabbed an off-the-shelf RPC server, you trip up on these things. So for example, you need a server that can hot swap in new models as you update them. Tastes change. You know, maybe next week, cat videos are going to be even more popular than they are now. Maybe next month, even more popular than that. You need to update your models regularly, especially if you're doing something adversarial like spam filtering. Right? Spam filtering models, maybe you need to update them daily. And the server needs to balance resource usage and latency while it does this. Loading a large model, for example, with too many threads might choke your serving. Right? It might lead to a latency spike while that new large model is being loaded. Or on the reverse side, when everyone gets home from work and opens up your app at the same time, and you have a bunch of extra requests to serve, and you're auto-scaling it up, starting new servers, you want those servers to start up as quickly as possible. So despite the fact that you'd want to load slowly while serving, you want to load with as many threads as you have while starting up your server. All right, next, you also need an API and a server that can handle multiple model versions simultaneously. You know, you want to be able to run experiments. You know, if you've determined that cat videos are going to be more popular next week, you probably want to test it on 1% of your users before pushing it out to everyone. Also, you might want to serve not just multiple versions of the same model, but multiple different models. If your app is predicting click rates for videos, somebody is going to optimize it to return clickbait, right? So you may need a second model to gauge the chance that I'll watch more than 30 seconds of your video, or a third model to tell whether or not I'll click the like button. You need an API and a server that can serve these three models together. Or in many cases, you can create a much more compact model by integrating these three models together, right? Having one model with three independent output heads. Right? Another thing we've worked very hard to solve with this TensorFlow serving program is batching. Right? Latency is very important for users in real-time applications. And it would be really easy to receive requests and push them into your model just as quickly as you get them. But batching can improve your compute efficiency hugely. Batching is like in my diagram here. We have 3 requests coming in, and instead of sending 3 requests to the model, we pack the 3 requests together and send 1 request to the model. This can have a huge impact on compute efficiency. On CPU, you can get something like a 50% speed up. On a GPU or our internal TPU accelerators, we've seen up to 25 times speed up from enabling this batching mode. And this batching is a non-trivial problem. If you have, this batching is a non-trivial problem. You have to queue up the batches of requests and choose which version of which model you should run next while trying to meet your latency targets. And so this is something we've worked very hard on to get it right. And that's what's in TensorFlow serving. TensorFlow serving sort of has 2 versions. There's TensorFlow serving, the set of libraries, right? It's a set of C++ libraries that include everything you need to build your own flavor of TensorFlow serving. There's everything you need to import or export a TensorFlow saved model, a generic core platform with pluggable interfaces. And one of the reasons we do this is because it's open source software, and so that we're not getting you into this locked-in position, right? It's called TensorFlow serving, but you don't even have to use TensorFlow with it. Right? These pluggable interfaces, if you have a legacy model built in a different system, you can build the plugin you need to run it inside TensorFlow serving. But if you're just using TensorFlow, we have precompiled binaries. They're easy to configure. They have best practices out of the box. They're all based on gRPC. We have reference Docker containers available and a Kubernetes tutorial that auto-scales up that inception model running inside of TensorFlow serving. So still got a couple minutes left. Good. I'll try to get through this last section quickly. Here we're just going to talk a little about how things are working inside of Google right now. By now you've probably heard about the computing power required to do these sorts of things, especially if you're dealing with these big video and image recognition networks. You may be wondering how much computing power does that take? At Google, we've wondered the same thing because we have lots of computers and lots of models to run. Right? I mentioned earlier that we designed these special purpose hardware. Right? Why did we do it? Because in 2013, one of our engineers sat down and asked himself, if every Android user uses voice search for 3 minutes a day, how many computers are we going to need? And the answer was we'd need to double the number of data centers that Google owns. So as an emergency project, they sat down, designed, built, verified, and deployed these things over the course of just 15 months. They had them in data centers by 2015. These first generation TPUs now support every one of those Google services that use machine learning that I was talking about, products used by hundreds of millions of people every day. They offer excellent compute and power efficiency, 15 to 30 times faster than contemporary CPUs and GPUs, 30 to 80 times more power efficient. But these are designed for inference, not training, right? So for running your model, for serving your model, but not building it in the first place. We like building big models, and that's the trend, right? Models are only getting bigger. So we have these second generation TPUs. Here I've added my manager for scale. These have pretty amazing specs, up to 180 teraflops per board. 64 gigabytes of ultra-high bandwidth memory, designed to do both training and inference, and to be connected together. And man, do we connect them together. That rack is about this tall. These TPU pods contain 64 of those new TPU devices. Altogether, this is 11.5 petaflops, 4 terabytes of memory on a 2D toroidal mesh. And what does this do for us? This lets us do things faster and better. It used to take us 24 hours on 32 GPUs to train one of our large-scale machine translation models. Now it takes us 6 hours using an eighth of this thing. Right? And why is that potentially relevant to you? It's because the TPUs are coming to Google's public cloud. Currently, they're not available. We're just gathering interest. If you're interested, let us know. We have 2 programs that are going to be coming out as soon as they're ready. The Cloud TPU Alpha, where we'll be allowing select users early access to the TPU platform, and the TensorFlow Research Cloud, where we're going to be giving free access to researchers to 1,000 TPUs. Free access to researchers who are willing to share the research when they're done. So very interesting, a lot of potential there. So that's basically all I have to say. TensorFlow serving you can find at tensorflow.github.io/serving, and TensorFlow itself at tensorflow.org or github.com/tensorflow. Or you can find us on Stack Overflow to answer your questions on the TensorFlow hashtag. Thank you.